thanks for the organizers for inviting me, and thank you all for patiently listening to me as lunch edges ever closer. I'm really thrilled to be going after Gigi because I think this is she said a lot of really important things that I will not have touched upon at all. So I think that's perfect. And also I want to echo her in saying that 20 minutes is not a lot of time to review a huge topic, but I've sort of stream of consciousness style put together some of the things that I've been thinking about recently and some of the things that I think we as a field need to be thinking about. And you can fight me on that later. I'll also highlight that there are several experts in the room and at least one on Zoom. Hi, Simon. You can fight with them as well. Okay, so I'm going to start with my philosophy in approaching this, which is that Lambda CDM is a really good model, right? In Lambda CDM, you have some galaxies, and we live here in this galaxy, for instance, if it's the Milky Way. And there is some halo, right? So we have the regular matter or baryons that are messing up all of my beautiful dark matter simulations. And we also have a dark matter halo that lives around them. And this has been pretty good on large scales, right? But I put it to you that Lambda CDM is not a great model because for me, it's not a great model until it tells me what dark matter is. I am just upset to not know what the majority of the universe is made up of. And so I care to know. And so for the purposes of this talk, we'll be living in this bottom corner of this wonderful diagram from Professor Tim Tate. So yeah, with that, let's start by talking about axions. So generally, there are two types of axions that people discuss. So the QCD axion, which Gigi just gave a wonderful introduction to, so CP violation, pitch equin, all of that stuff. And sort of she introduced the idea of FA and how that sort of sets the mass of the axion. So basically, if you want this to be below Planck scale, you want the mass to be sort of like greater than 10 to the minus 12 eV or so. So these are light particles, of course, but they're not ultralight in the sense that I will be discussing them. On the other hand, we have axion-like particles, which are sometimes called ALPS. I'm lazy, so I just call them axions a lot. So these are pseudoscalars that arise from different BSM physics. So for instance, from string theory, so that sometimes earns them the name of string axions, through string theory, but also just other extensions, other sort of like quantum gravity visions. You can produce hundreds of such fields, and they can pick up a variety of small masses sort of on this range, right? So that's a pretty large swatch of space to be thinking about in terms of parameter space. So let's narrow that down a little bit, maybe. So if you're all the way on the right over here, you might be thinking about the QCD axion. And so you might see exclusion plots that look something like this. This isn't the latest and greatest one, but they are all sort of similar, where this yellow line is the two sort of like very theoretically motivated sort of models of the QCD axion. And so you're looking for some axion that has some mass and a related G alpha gamma gamma, which is its coupling to the electroweak sector, which is to say, once in a blue moon, an axion will turn itself into two photons, or two photons will turn themselves into an axion. And so you look for this, astrophysically or with all of these wonderful haloscopes and stuff like that. On the other hand, if you go to the other extreme, sort of on the order of 10 to the minus 33, the axion hasn't entered that oscillating phase that Gigi told us about yet. And so they basically act like dark energy. And so that means that we don't really care to be thinking about that if we're thinking about dark matter. And also at some of these super light cases, you basically get constraints from large scale structure because remember, Lambda CDM is a good model. And by the way, when we're talking about this still remaining swatch of space, especially here sort of between 10 to the minus 18 and 10 to the minus 10 or so, or even higher, that is basically CDM, right? That it acts like, it walks like a duck and it quacks like a duck. It's just a little bit more defined than a duck. So is all of this free real estate? No, of course not, because this is physics and nothing is good. This is a figure from a wonderful review article by Lisa Ferreira that is, going on 5 years now. So these aren't all of the mass exclusions that exist, but they are many of them. So I would like to highlight that a lot of these, they're not terrestrial experiments, right? Because of the masses involved, it gets very, very hard to build say a haloscope at this range. So these are mostly coming from astrophysical probes that are often, sort of come from predictions of phenomenology from simulations, right? Which is what we're talking about today. I'll also note that here this says FDM, standing for fuzzy dark matter. So that's not axions in general, and we will unpack that in a moment. But also I will encourage you to see Kier's website for better, harder, faster, stronger limits that are more up to date, because there's some really beautiful plots on there. Right, so let's talk about terminology. I think terminology is one of the things that this subfield really, really suffers from, and I only recently sort of sat down to disentangle it a bit for myself. There are several asterisks up there for a few reasons, one of which is that this is the terminology as I have decided to look at it recently, and so not everybody agrees, but also we must all be aware that we are sort of always in the phase of producing terminology. Every new paper that makes a decision on what to call a particular thing is sort of contributing to the conversation. So this is not static. What I show you may be wrong immediately or very soon or something like that, but just, buyer beware, I guess. So let's start with ALPS, right? That's what I said, axion-like particles. So not the QCD axion, but a more general idea of an axion. Inside we have fuzzy dark matter, right? A lot of hay has been made about fuzzy dark matter by a lot of people, myself very much included. And there is sort of something in between ALPS and fuzzy dark matter, which is sometimes called ultralight axions, which is almost the same, but not quite. So it's a little bit wider than FDM in that it assumes, it allows for the possibility of non-gravitational interactions, right? So ALPS, a very general term. Fuzzy dark matter, sort of a specific candidate with this mass on the order of 10 to the minus 22 eV, because then you get very particular phenomenology, and it's generally one particle only. ULA's ultralight axions the same, except we can also have non-gravitational interactions, so the particle can interact with itself, right? Self-interacting axions. All of this I wrap in sort of this larger circle of several terms that I consider mostly degenerate. So when I say ultralight dark matter, I sort of like encapsulate all of these. So anything that's lighter than, say, that QCD axion. Sometimes you hear wave dark matter, which it's wavy because it's light. It becomes so light that end body stuff isn't really useful anymore, and you start thinking about it in terms of waves. So that I find that kind of degenerate. Sometimes you see it called psi dark matter for the same reason. You're thinking of a wave function. And also Beck DM is Bose-Einstein condensate dark matter, which it's wavy, it's bosons, it forms a Bose-Einstein condensate. Caleb.
I think WDM is like lawful evil.
Lawful evil, okay. Because it can be warm dark matter? Yeah, fair enough. I have seen it used, so I put it here. Straight to jail, okay, bye, yeah. I am telling you that I find them basically synonymous. You are free to disagree with me. But I find them, sitting down and thinking about them, I find them basically synonymous.
Very naive question.
Yes.
Someone outside the field. In my particle physics brain, anything that's astrophysically fuzzy is fuzzy dark matter, but I guess anything that's astrophysically fuzzy is also astrophysically wavy. So what's the...
So hence it's a subsection, right? So it's a subsection of wavy dark matter, because you can be wavy but not be fuzzy. Right, you can be wavy, but have a particle mass of like 10 to the minus 17 EV, not talking about whether it's excluded or not, which is still wavy, right? I still use like a pseudoscalar solver or something like that.
Okay, so wavy in the sense that I have to worry about patterns within the halo, but the halo as a whole is still static.
Yeah. So the way I think about it, fuzzy is really when you get that Bose-Einstein condensation on the order of like about a kiloparsecs. So you think about like solitonic cores. Solitonic cores are the name of the game for fuzzy dark matter. You can be wavy, but at a higher mass such that that solitonic core shrinks. And so that's maybe not something you're worried about because it gets like eaten by your black hole or something. This is good. I like the discussion. Other comments, questions? Okay, sweet. So you could also say scalar dark matter and vector dark matter, which are slightly different except when they're not. So they are more general terms, but they sort of interact with this, because we have scalar, all of these things are scalars, so they are some subsets of scalar dark matter. And vector dark matter can basically be thought as mathematically equivalent to 2s plus 1 scalar fields, where s is the spin. So I'm thinking here about work by Mustafa Amin and colleagues. I know very little about it except for this statement. Okay, can we accept that terminology at least for the length of this talk? Cool. All right. Something went wrong here. Nice. Okay, I'm somehow missing a slide, so you're just gonna have to use your imagination, okay? the terminology sort of extends a little, or the terminology confusion, I should say, extends a little bit to the system of equations. So let me pretend I don't have this lambda here, and that nothing is crossed out. So this would be the Schrodinger-Poisson system of equations, right? It's psi dark matter, it's wavy, whatever. So we think about wave functions that we evolve forward with our Schrodinger equation that is coupled to phi, which is the gravitational potential. The gravitational potential is evolved with the Poisson equation, which in turn depends on the density, which is also involved in the, or which is set by the absolute value of psi squared times like the mass of the particle. So that's a Schrodinger-Poisson system, and this is, this is more general than FDM. FDM says that this mass of the axion is on the order of 10 to the minus 22 eV. That's sort of the canonical number that I go by, but there's some range there. Now, if you add this lambda, which I think I'm missing some factors of 2 and m cubes, which is what I get for making this talk at 1 a.m. But if you add this lambda, basically this says that there is another term in the Schrodinger equation that says that the field can interact with itself, right? There is some lambda, which is a strength of a coupling. Like I said, there are some twos and masses, but that only depends on psi itself. And so in that case, you have a more general version of a Gross-Pitayevsky-Poisson system. So if you go to your colleagues in like cold atom physics, they are much more likely to react to this name than to the other name, because there are some interesting sort of cross-pollinations to happen there. Maybe not with the Poisson equation, but certainly with the Gross-Pitayevsky equations. And those are like ultralight axioms, right? Because we've introduced self-interactions. Yeah, and most of those mass exclusions that I showed before don't include this. So a lot of the mass exclusions, not all of them, of course, but a lot of them do really assume FDM, which means that many of them assume that it is all of the dark matter. Some put limits on how much dark matter it can be, but that is sort of more recent. For a while, it was an all or nothing game. And most mass exclusions do not include sort of the possibility that there are non-gravitational interactions, which there could be. Right, so now thinking about fuzzy dark matter, I stole this from a paper of mine because I wrote it with an astronomer, which means it has actual units, which is extremely rare. Just to sort of show what a fuzzy dark matter halo looks like, right? So this is the density profile as a function of radial distance here in kiloparsecs. And so the two things to notice with FDM halos, the two things that we sort of look for, and what most of the mass exclusions are based on in one way or another, are this solitonic core. So this is this core that we get, which has sort of been, originally was touted as like a, hey, here's a solution to the core cusp problem. Now we maybe care a little bit less, but nevertheless, that's why one of the reasons why it originally got popular, at least. And then we have this turbulent skirt on the outside, which doesn't look that turbulent here because it's a static image, but I'll show you more in a second. And so the size of this soliton core, which here is shown as RC, which is like the full width half max, really depends on the mass of the axion itself, because it basically is said by the de Broglie wavelength. It's how big is your Heisenberg uncertainty principle, right? So the more massive a particle is, the more localized you are, and so the core shrinks and you sort of go out of that fuzzy dark matter regime. The lighter it is, the soliton grows and grows and grows, and finally you have halos, you're predicting halos that should look like solitons, which we kind of know isn't the case. That's, we feel pretty good about understanding dark matter of large scales. And yeah, and both of these can be impacted, for instance, if lambda is not equal to 0, right? So both the profile of that soliton core changes and the sort of interference fringes will change. So now I will follow the great path set before me of this is a simulations talk, here's a simulation. So this is one of my fuzzy dark matter simulations, which is really just for show. So what happens is that I make a fuzzy dark matter halo here by merging two of these soliton cores, and you just get something that looks like a halo in the end. Ooh, pretty shiny, shiny. The point is that we can see this soliton core at the center, and we can see both constructive and destructive interference here, understanding that lighter colors are denser and darker colors are less dense. And so all of this constructive and destructive interference basically is that turbulence of the skirt. And so that is what you might use to say, set limits on the particle mass, thinking about dynamical heating and friction and stuff like that. So just to show a little more specifically what the pheno considered here is. So this is a definitely incomplete list of fuzzy dark matter and ULDM simulation tools. Like most things in life, it runs mostly on nepotism because these are the things that I have used or directly know about. But there are many, many more. So for instance, this is a talk that Jiajun Zhang gave in 2019. And so you can just see the number of different simulations here. And that was, 5 years ago, almost 6 years ago at this point. So the number and quality of fuzzy dark matter simulations is growing, and that's really exciting. That is something that is pushing the field forward. However, I was worried that I would come off as too negative until I heard everybody else's presentations. So I feel that we are on the level. However, I really cannot stress enough, and I know I'm preaching to the choir here, but I cannot stress enough how much we need to approach these simulations critically, right? Especially since you can't see dark matter, right? And so what we're really doing is trusting the simulations to work to make predictions that we can then test against the universe. But first, those simulations have to work. So a question to ask is, do they match each other, right? And so for a long time, and still probably, the answer was no. So this is my favorite example because I wrote a paper on it. That illustrates, so all of these three figures show the same thing. I'll start with the one on the right just because it has, maybe it's the most clear. So what this is showing is the mass of the core, so the mass of that soliton as a function of the mass of the halo divided by the mass of the halo. So basically, how big of a core do I expect in a Milky Way versus like a dwarf halo or something like that. And on the x-axis here, what we have is some parameter psi, which is what was said in the literature as like, the absolute value of energy over mass cubed, and then with some parameters that make it unitless. So basically, how can I sort of describe my halo with a convenient number without thinking about it too hard? And so what we see here is in these three works, starting with Shrey et al., that sort of like, to my mind at least, really started the boom of fuzzy dark matter simulations with their wonderful simulations back in 2014. And with, say, Schwabe and Mox, both people that have done really wonderful fuzzy dark matter and ULDM work. So in each of these cases, the answers don't match. So, and this is like a really foundational prediction, right? It's really important that I understand how big of a soliton core I expect in a halo if I'm going to be making exclusions based off of that. So maybe we don't understand the core halo mass relation, as it's called, as well as we thought 5+ years ago. So this is the paper that I wrote on it, but I'm not at all the only one. There are many, many refs in there of people doing fantastic work showing that a lot of this difference is not just due to the history of how these halos evolved, which is important, but also due to things like numerical friction. So not a function of the universe or of the dark matter candidate itself, but the function of the fact that I am a simulation in a box and the universe, to the best of my knowledge, is not in a box. So it is really, really important that we be careful about numerical versus physical signs, especially in something like fuzzy dark matter. Yes, of course.
So, I mean, we've heard a lot about getting statistics from simulating many samples. Sorry. I should know better. But in these simulations, does it have bells and whistles like baryons and all that kind of business, or is it all just?
No, these two certainly don't. I don't think this one does.
Okay, so this is pure fuzzy dark matter.
It's pure fuzzy dark matter. This is more of a cosmological simulation. This, to the best of my memory, are not cosmological simulations. So there are definitely sort of like, there are asterisks here. Right. There are things, it's not completely an apples to apples comparison. Yeah. The other thing is, it is not clear how each of them define, for example, a halo mass. So also in the definition of very basic parameters, it's not clear that there's agreement.
Okay, fair enough. But I guess my sort of zero thought question is that, like in the sort of real simulations with baryons, et cetera, then we keep learning that variance between galaxies is important. You have to run many sims to get an idea of the spread and so on. Is any of that a factor here, or are these simulations so simple that it kind of shouldn't be?
You really made my transition to my next point wonderfully
Excellent.
well.
Thank you.
No, that's great. Thank you so much. So hold that thought maybe just for a moment, and hopefully I will answer it, and if not, pester me again. So I would like to highlight that sort of fuzzy dark matter or ULDM simulations in general have some really unique challenges. So we kind of started from the fact that the less massive your particle is, the more you have to put, the more of them you have to put into a halo to make, sort of 10 to the whatever solar masses halos, right? That's just math. We are in the Fields Institute after all. And so that makes for wave-like dark matter because you're solving these Schrodinger-Poisson or Gross-Poitevsky-Poisson, however you like, equations. And this is not an n-body thing, right? So you're solving, for the most part, at least pseudospectrally. Furthermore, these equations are not linear. They have a lot of del squareds, which are a pain. So even when doing something like doing very clever things like calling on FFTW, which is maybe my favorite named sort of like numerical package, the fastest Fourier transform in the West, this is the slowest step, right? And it just always will be because del squareds are expensive to calculate. But first, okay, Caitlin, sorry, don't kill me for this. But also because it's wave-like dark matter, the maximum step time, it has a very specific scaling, which comes from the fact that because it's a complex field, you can't have your phase varying by more than 2 pi between, or more than pi or something between two adjacent grid points. Otherwise, you see the particles moving backwards in time, and that's not great. So here, L is the size of the box, and NG is the grid size. So at the same time, so that sets your maximum time step, right? And so you have to run a lot of these to run your halo for a long time. So at the same time, the soliton is tiny compared to the box, which means that we want a really large box to fit a really large halo in and really fine NG to resolve the core, which you're shaking your head. So I think you're getting the point. So TLDR's pseudospectral simulations are really expensive to run, and they're sort of expensive in a qualitatively different way than n-body simulations. And because they're different, it's kind of hard to I don't know, attach yourselves to sort of like ride the coattails of some of these like really wonderful big n-body simulations. So it's even harder than something like SIDM. So basically, what does this mean? It means it's harder to compare with CDM and other alternative DM sims because it's not quite an apples to apples comparison, right? You can't run a suite of like CDM and SIDM with like different, different particle masses and also FDM because it's a qualitatively different way to run. It is harder to benchmark against a range of baryonic feedback models because they're so expensive, and so you need to run a lot of them. And sometimes maybe you have better things to do or not enough computing time or whatever. And it's harder to run for a range of possible models. So here I'll highlight again that there can be self-interactions, but also calling back to that first slide of sort of introducing ALPS, there could be hundreds of them. So it's not clear that if string theory, then one axion. In fact, it's quite probable that if string theory or an equivalent BSM that sort of predicts these scalar fields, probably many axions. And that just means more and more fields to run, right? So to say, sort of, I hope that this answers your question a little bit in saying that it's very expensive. People have done amazing work. Simon, who's on the call, has done some really fantastic simulations and stuff like that. I'm not negating any of that, but we just have the deck stacked against us in comparison with n-body simulations, for instance. So in comparison with SIDM and warm dark matter and stuff like that. And yeah, so remember those hundreds of axion fields? So what if we live in an axiverse, which is my new favorite thing to think about? So we need even more time and memory because now we have sort of the same set of equations, except that we need to evaluate J axion fields, so whatever J number there is. And they can have both self-interactions and interfield interactions that are non-gravitational. So here, all of the fields are sort of coupled through the Poisson equation, but you also have this matrix lambda that basically tells you how each of the fields interacts with itself and how it interacts with the other fields non-gravitationally, which is not forbidden and can happen, right? And this is actually really important. So this is a work. So my understanding is that Chandra Prescott-Weinstein was supposed to be giving this talk, so she would have done a much more fantastic job than me. But I'm very happy because along with her and some wonderful colleagues, Nathan Musoki, Anthony Mirasola, who's on the job market, please hire him. He's amazing. And Mark Naring, we just put this out, which is that in an axiverse, we can completely break the expectation of a solely solitonic core. So what I'm showing you here upstairs is in a case of just two axion fields with some mass ratio that is relatively small and some repulsive interfield separation, you can really change the ground state profiles of what those look like. And this translates very directly into the density of the center, which is shown here in the black lines. In the gray in the background is showing two solitons of like either just a single field mass or a double field mass, right? And so you can go from something that is much cuspier or rises much quicker than a soliton to something that is vaguely solitonish, even though both of the fields are kind of weird, to something that is not even spherically symmetric. And so again, I think this is kind of important, and I think these kind of predictions are crucial for carving out the allowed parameter space, which quite frankly becomes huge, because now not only do you fall off from a lot of those mass exclusions, right, because you're not in the FDM space, even so, you still have a range of masses for each of the fields, the range of number of fields, and the range of both self-interaction and interfield interactions. So these do not contain any self-interactions, which could change the picture. But also, none of this, not to be too down on simulations, we wouldn't have these kinds of predictions without simulations. So I just wanted to say, don't panic. This is my cat, Fat George. Don't panic. There's a lot to do, but we can and we have historically been creative. And I think that, a lot of people in this room and a lot of people not in this room, together we can do some really interesting things. However, we need to be careful with how much we trust the computer. Nobel Prize be damned. So what I hope you take away from this talk is a better understanding of the ULDM name salad and state of the field. Even if you don't agree, that's totally fine. I'm totally happy to discuss it and change my mind. Again, it is a living document and something that we are all building together every time we use it. The vast majority of FDM mass exclusions are sound, but many don't include self-interactions or more than one axion species, and some, but not all, assume omega dark matter is omega FDM, meaning that all of the dark matter is in a single axion of the fuzzy mass. So this could impact our results a lot, and changes the, all of these things that they're not assuming. They can change the two basic FDM observables, like solitonic cores and turbulent skirts. By the way, I didn't precisely mention this, but those solitonic cores kind of correspond to the cutoff in the power spectrum, right? So those are the scales in which you wash away structure. So they don't just appear when you're, say, fitting profiles of galaxies or something like that. They can also appear other sneaky places. And so, in fact, given the landscape of mass exclusions, these may be the way we're all headed soon. So simulations are still our best way of translating theory into observable predictions, but we really need to interrogate the results critically. And I think benchmarking against other simulations is one good way to do it. And I just think that numerical resource requirements, at least to my mind, means that we're nowhere near the quality and quantity of CDM and, say, SIDM simulation suites. But we'll need to be a little bit clever and a little bit creative and figure out how to seriously stress test these models, especially in presence of baryonic feedback models, because if there's anything that I've grown more and more convinced of with time, and especially in this morning session, is that baryons matter a whole lot. And you can only get so far with just simulating dark matter, whichever candidate it is. Yeah, so I'll end there. Yeah.